Next, we're going to look at gas exchange in different types of organisms and how efficient they are. We'll start with fish. This image shows a fish and the flow of water, which comes into the mouth and then flows out of the organism through the gills. It actually leaves the organisms by flowing underneath the opercular flap. And so this is that flap on fish where you can lift it up and it looks like a slit. Underneath there are the gills. Water needs to flow in this pattern, a unidirectional pattern, passing over the gills because the water is where the fish get their oxygen. So we see that as the water flows through the individual, it's going to pass over the gills and come into contact with these filaments of gill arches. And this is what we took a look at in the previous video. If you remember this, we saw these very, very thin structures with a very high surface area. And this is actually where the gas exchange occurs. So in the fish, surface area is maximized. The distance over which the oxygen needs to diffuse is maximized because this tissue is very thin. The flow is somewhat maximized because it's unidirectional and the flow comes in the mouth and out through the opercular flaps, and this especially occurs when the fish is swimming or moving, or when it opens and closes its mouth. It could force the water through. The concentration gradient is also maximized because there are blood vessels all throughout these structures, which can take the oxygen from this area and then move it away. And we will talk about countercurrent exchange in a moment. The thing that's not maximized is the water or the substance rather, that fish are breathing, and it's not maximized in the sense of Fick's law. It's much more efficient. You could get the maximum amount of the maximum amount of oxygen if you're an organism that's breathing air instead of water. And so I want to take 1 minute and go back for a second, look at these gill arches, and show you exactly what we're seeing in comparison to this image. So these gill arches, we see that there are lines here, and those lines actually represent these filaments that we saw on this previous slide. And these very, very thin pieces, we actually can't even see in this illustration because they're just so thin and very, very small. So again, we don't see them here. This is an image from under a microscope. Now we're going to go back and talk about everybody's favorite subject, countercurrent exchange. I've even made an advertisement for fish for countercurrent exchange. Most fish do have countercurrent exchange, but just in case they don't, they should get it. So previously we talked about countercurrent exchange with respect to temperature and conserving heat. Now we're going to talk about it in terms of conserving oxygen, or really maximizing the amount of oxygen that a fish can get out of water. We see the setup here. It's a little bit more complex than what we talked about with the countercurrent exchange with heat conservation. We have a couple different things going on. We have water. Water is moving from right to left. We have blood vessels flowing into the gill area. We have blood vessels flowing out of the gill area. And then we have more blood vessels which are flowing across those lamellae. Again, the lamellae are the very, very thin sections of tissue where gas exchange actually occurs. So this is the only place where blood can actually receive oxygen at the optimal rate, because that's the only place where the tissue is that thin and has that much surface area. So going back to this image, this is where the exchange is actually taking place for the most part, and it is set up this way for a reason. As we see, the blood that is coming in has already had the oxygen delivered to the tissue, so it's very low in oxygen. It's called deoxygenated blood, and it's entering the gills here. This blood vessel here is exposed to the water. It's exposed to water that has already had a lot of the oxygen extracted on the right side. We'll talk about that in a moment. But this is good because if there's going to be any oxygen exchange, it's going to be going from the water to this blood, because this blood just has so little oxygen because all of it was delivered to the body. So this is great. This is maximizing the amount of oxygen that's taken out of this water. Then on this side, we are minimizing the amount of oxygen that's lost to water, because the blood will flow into these lamellar gill filaments, this tissue that's very thin. It picks up oxygen from the water, and then it moves in this direction from the bottom to the top of the image. And as we see, as it moves through this blood vessel here, it is exposed to water that has just entered the gill. So that's water that still has a lot of oxygen in it. So again, in this instance, if there's going to be exchange, it's going to be from the water, which is higher in concentration of oxygen, to the blood, which might be slightly lower. This entire system, therefore, maximizes the amount of oxygen that can be extracted from water with this setup. So that is for fish. Now let's move on to mammals. I realized on the previous slides, or for the last few seconds of the video, that little message was up in the corner for some reason. You can just ignore it. This program's driving me crazy. All right, so gas exchange in mammals, really different than in fish. The entire setup is different right from the start in terms of getting the substance that we're going to extract our oxygen from. Again, we said fish do this by letting the air flow over the gills as the fish moves. We, of course, don't do that. We breathe in and we suck air in by expanding these muscles, and we'll talk about that in a moment. But I do want to point out that the layout is similar, or there are characteristics of the layout in the process that are similar, because we are again maximizing surface area, because we have so many chambers where gas exchange occurs. They're very small. We'll talk about that in the next slide. We also have a very short distance over which the oxygen needs to flow or diffuse, because the tissue, again, is very thin. The flow is maximized because, again, we have the blood taking oxygenated, blood flow away from the lungs, taking that oxygen to the body. And unlike fish, we are actually maximized in terms of the substance that we're breathing, because it's air, not water. What is not maximized in the lungs is that there's dead space, because it is technically tidal flow, which means that the substance moves in and out of the same openings. So we have air coming in to and out of our nasal cavity and our mouth. So let's take a closer look at the tissue that actually makes up the lungs. So this is just a schematic, but I wanted to show this because it shows, similar to the instance with the fish, there's a lot of branching in the lungs. And the air comes in and goes out of this area here and travels down the larynx. And then we see that there are a lot of branching structures in the bronchus, and these bronchi branch over and over again. They kind of look like little plants or roots or trees. And then at the end of each of them is where we actually see these structures where gas exchange occurs, and these are called the alveoli. Now, due to the extensive branching, we have increased surface area, of course, but in addition, that's not as important because gas exchange doesn't actually occur in these bronchioles. The gas exchange occurs in alveoli. So the branching of the bronchioles is important because it creates more endings, or endings like dead ends in the lungs, and that's where these alveoli are. And this is an image of a cross section of a lung or lung tissue, again under the microscope. And all of the white spaces are areas where there are one or more alveoli, and that's where gas exchange is actually occurring. You'll notice that this looks a little bit like a sponge, and the lungs truly are made a little bit spongy because there are so many of these empty cavities where, again, we have tissue that is very thin and where oxygen can diffuse from the air that's being brought into the lungs, into the blood, and then carried away, as we see here. So there are millions of individual pockets of alveoli for gas exchange, again, increasing surface area. And these are also very thin, as we could see. They maximize or minimize the distance over which oxygen needs to diffuse. Similar to the fish as well, and I'll enlarge this a bit, we have oxygenated or deoxygenated blood coming in, flowing over, and then flowing out, so that all the oxygen, which is taken up by the blood, is going to go to the heart and then to the tissues. So we're taking the oxygen away from this area again, so it doesn't diffuse back into the air. So we're maintaining, keeping up that concentration gradient. Now let's talk a little bit about the way that we actually get air into our lungs. Not necessarily oxygen, but air in particular. So air is drawn in and expelled out by the diaphragm and intercostal muscles. And these are muscles that are in between your ribs, which are shown here. It's right here. And unlike the fish, obviously, we don't have oxygen just flow over our lungs and then exit from a second opening. We only have one opening, essentially. And we have our nose and our mouth, but they both lead to the same junction, or they have a junction so that they both lead through the same apparatus, or the same path to get to the lungs. And then the air needs to come out the same way. So during inhalation, we're not actually forcing air. We have the diaphragm contract, and so this is a muscle, and as it contracts, it creates a slightly larger space for the lungs, and so it creates a little bit of a vacuum, and it lets this cavity expand, and so we draw air in. If you're familiar with the concept of like snaking a hose, or using some sort of hose or tube to get water to suck out. So I'm thinking in particular, when I was growing up, we had a pool, and it was an above ground pool. It was extremely old, but that's not related. And we would put a cover over it during the winter. Then in the spring, there would be all this water that had pooled on the cover, and you would have to draw it off somehow before you could take the cover off, because it was too heavy to lift off, and you didn't want to just slide the cover out, because then you get all this dirty rainwater and whatnot from the winter in the pool. So that's gross. So what my family used to do was, my dad would get a hose, put one end in the water that was sitting on top of the pool cover, and then he would suck on the hose as hard as he could, and it would eventually create enough vacuum so that it started drawing the water from that pooled water on top of the cover out. And so it would go for, minutes at a time once you got that flow going. So this is similar to how we get oxygen into our lungs, or how we get air into our lungs. By the way, when my dad did that, it was the grossest thing ever, because that water was gross. But that's besides the point. Yeah, so that's how we actually get air into our lungs. It's through negative pressure. And then we need to get rid of the air, which now contains a high level of carbon dioxide, because we've exchanged the oxygen. It's gone into the blood. Carbon dioxide has come out of the blood. And this is when the diaphragm relaxes. So this muscle now relaxes, and it makes this cavity slightly smaller. So then it's going to actually push some of the air out. And your lungs contract, and that allows the gases to be expelled. I also want to talk a little bit about something that you may not be familiar with, which is the coating around the lungs. And so the textbook mentions this. This is the pleural membrane, or the pleural cavity, and this is really important. It surrounds the lungs and helps them maintain structure during this period when we're breathing out. And we can see that the pressure inside of the alveoli and in the pleural cavity rises and falls in the same pattern, but the pressure in the pleural cavity is always less than in the alveolar cavities, which means that it's always going to be pulling out a little bit on the lungs. So again, the lungs don't collapse. And the book goes into a lot about how this membrane interacts with the lungs, and how the two surfaces slide over one another while they're still in contact. And so it gave the example of two microscope slides that got wet, and they're really hard to peel apart. If you're not familiar with that, just think of when the pages of a book stick. So when the pages of a book are stuck together, sometimes you could kind of take your hand and slide them back and forth, but you wouldn't be able to grab one page and pick it directly up off of the other. And it's kind of similar to the concept of the interactions between that pleural membrane and the lung. The two can slide back and forth, but you can't peel them apart because of that negative pressure unless there is a puncture in the membrane, and that is what causes a collapsed lung, and that needs to be dealt with, or else it has really serious consequences.